Okay, so if you have the note guide, this is in the note guide. If you don't have the note guide, you just put it where you're taking your notes. And basically, here's the idea. We're going to go through parent functions and functions like you did in Algebra 2. But we're going to do 2 a week. So this week, we're going to do quadratics and cubics. Next week, square roots and cube roots. And then it'll take us a couple weeks to do log and exponentials because they're a little more difficult. Okay? So we're going to approach them like you guys did in Algebra 2. So if you look down, just a second. If you look down the page, you'll see this looks like what you guys did in Algebra 2, those Cartesian catalogs every time you learned a new function. We're going to do this at the beginning to kind of remember, what we were supposed to be doing. But really our focus is going to be 2 things. Graphing. Can you guys not take me seriously? I'm trying to teach math. Okay. Graphing. And then we are going to find intercepts and talk about domain and range. Okay? That's going to be our goal. Don't laugh at me. Okay. All right. So first thing we want to do is just remember what the parent functions were for these. And based on the feedback that you guys gave me of what you did in your Algebra 2 classes, every teacher started with the parent functions with like the tables for these. You guys all knew that at least the parent function had a table. So if you remember for your quadratic function and for your cubic function, these were the numbers we plugged in to build the table. So you either need to memorize for the first time if you never did in Algebra 2, or re-memorize because you did in Algebra 2 but you forgot, like who holds on to this forever, right? The parent functions, and that can be memorization by like straight up, like I just recall this whole chart in my head, I don't know where it came from, but I just memorized numbers in it. Or remember that basically for both of these functions, we're using -2, -1, 0, 1, and 2. And for this function, we're just quickly squaring those numbers. And for the other function, we're just quickly cubing them. So for when we're squaring, those are our y values. And when we're cubing, these are our y values. Okay? So again, how do I know this? I either memorized it, or I just know to use -2 to +2, and then quickly plug them into either square or cube, something like that. Okay? And then go ahead and plot those points on here so that we can have a graph of the function. Now I'm going to do the same thing up here. And then hopefully you'll see the difference in shape. Like that. Okay. I'm going to first time so you remember that we had these ideas. So focusing on the quadratic first, we're going to go through. So for the parent function, our vertex or our HK values are at 0, 0. What about x-intercepts and y-intercepts for that quadratic graph that you see? Yeah, so it nicely just hits kind of right at the origin. We don't have to do any algebra to get those calculations. We can just read right off the graph that it's 0, 0. And that's what's nice about a parent function. That's why we always start with them. They're kind of like the simplest function you could create in this shape. Okay. All right, domain and range. So first, domain. Good. All real numbers, okay, -∞ to infinity, depending on how you like the notation. Okay, and then what about the range for the graph? So you have the graph in front of you. So looking at it, what do you think, Olivia? Good. So it has a minimum at 0, greater than or equal to 0, or I heard someone say 0 to infinity. And that 0 would have the square bracket because we actually hit 0. So the increasing, decreasing intervals are a little bit kind of weird. I don't know if you guys remember them from Algebra 2. So I'm just going to give like a brief explanation. So first, to identify what's increasing or decreasing, you look at the graph from left to right and imagine yourself being on the graph. So if I was on this parabola as I moved from left to right, I would be going down. I would hit the turning point, and then I would be going up. So I would be decreasing, then I'd hit this little lull here, and then I would be increasing. So like this is the decreasing part of the graph, this is the increasing part of the graph. Okay? They both have arrows that go up. It's not about where the arrow goes. It's about if I'm going from left to right and I'm on the graph, that part's going down and this part's going up. But the way you write it is weird. You write the x's that it corresponds to. It's kind of like restrictions for piecewise functions, right? You look at the piece on the graph and you go back down to the x-axis like you guys were doing yesterday on your Desmos activity to decide the restrictions. Same with increasing and decreasing interval. You know that this whole part right here is called decreasing. Which x's does that respond to? So the boundary is at 0, and there's no left side boundary. So that would mean all of these x's over here make the graph that is decreasing. Okay? So the way that we would say that is we say from negative infinity until 0. And I'm saying 0 because of the x value, not because of the minimum of the graph. It's important that we recognize that. Okay? So then what would my increasing interval be? What are the x's where the graph acts like an increasing kind of thing? Good, from 0 to infinity. Oh, thank you. Sorry, you guys have to change it too. Sorry. Thanks, Will. All right, so I said the right thing, but I was writing it in the wrong spot. Did you guys make the correction so that we have in the right spot when you look back? All right, does anybody remember what 1-to-1 meant?
1x corresponds to 1y.
Good, 1x corresponds to 1y. So not just the vertical line test, the function, but also the other way. Like it has to pass the vertical line test and the horizontal line test. So is a quadratic 1-to-1 a parabola shape? No, because it fails the horizontal part of the test, right? Rate of change you guys aren't going to have to write about here. If you decide to take a path towards calculus, you guys will do some calculating of rate of change. So generally you guys just wrote down something like varies. I won't ask you about that. Okay, axis of symmetry for this. So it's at 0, and it's important the way that we say it. No, were you going to answer? Sorry.
Yeah.
Good. Okay, but notice he says x is 0. That's super important. The axis of symmetry is a vertical line. It needs to be named with a vertical line equation. Okay. And then minimum value and maximum value are just talking about y values. So in this parabola, there isn't any maximum. It keeps going up towards infinity, so we say none. But it does go as low as 0, so the minimum value is 0. And then asymptotes don't apply to this function. You can literally cross it out or write not applicable. We just are keeping this whole setup because we want it to be familiar with what you guys saw in Algebra 2, and we use this for every function there. All right, do we kind of remember the shape of a quadratic, that it has these characteristics, and our focus, you guys, is going to be right here. We are going to mostly focus on intercepts and domain and range, because intercepts involve solving later, and domain and range is something we consistently have to know about. Okay, so we're not going to ask you everything all the time. We're going to have a big focus on these things. Okay? That's good news. You don't have to write all these characteristics for every homework problem. Okay? All right, so now let's try and go do the same thing for the cubic. Okay, so new people every time. Let's go through all the characteristics and see who can tell us what. All right, so HK. Somebody raise your hand and tell us that. Aaron? Good. 0, 0. This function kind of centers around 0, 0. It's not really a vertex. They actually call it, I don't know if you guys care, but they call it like a point of inflection, where it kind of tricks you, like it looks like it's going to turn around like a vertex, and then it doesn't. It has this like weird lull. They call that point of inflection. All right, somebody else, x-intercepts. Paige. Good, 0, 0. And y-intercept. 0, 0, right? These are the easy ones. You guys got to get those ones, okay? All right. Domain. Who can raise their hand and tell us domain that hasn't told us anything for this function yet? I didn't see anyone's here. They'll have it. Yes, Ainsley. Sorry. Good. Okay. I didn't startle you, right? Your hand was going. So all real numbers are negative infinity to infinity. You can plug in any x value and cube it. Okay. What about our range, our y values for the cubic function? Somebody new, raise your hand and tell us the range. Yeah, it's good. Okay, all real numbers again, because this doesn't turn around like the parabola. All right, who thinks they can give us increasing interval? Olivia?
0.
All right, actually even more than that. It's super tricky. Yeah, good. Negative infinity to positive infinity. Because if you were on this function the whole time you go from left to right, you would be climbing, like you'd be very tired, right? Okay, climbing the whole time. So the whole time you are increasing, which means you don't have any decreasing interval at all. Okay. All right, somebody new, is it 1 to 1? Yes? Okay, how did you know, Joe? Good. So for every x, there's one y, and for every y, there's one x. You could run horizontal and vertical line tests on this, and it would pass them both. Okay, again, rate of change is not really our concern here. We don't say it has an axis of symmetry. I know it has some symmetry, but it's more of like a rotational kind of symmetry. So an axis of symmetry is like we just want to identify a very simple line we can fold it on. So for this, we won't. What about our minimum and maximum values? Paige? Good. Okay, we actually just write none though because they want an actual number when they say the word value. It's weird like terminology, vocabulary kind of thing. It goes from negative infinity to positive infinity, and because of that, we cannot list an actual value as the maximum or minimum. We just say none. And then again, no asymptotes for these functions. Okay? And one more time, our emphasis is going to be on intercepts, domain, and range. So does everybody feel like they're having little Algebra 2 flashbacks? Like, oh yes, parent functions, some properties, and stuff like that, okay? So we're going to go through, and we're going to graph new versions of these with transformations, okay? So on the next page, we see two new functions, a little more complicated. And we're going to start with the quadratic. So if you don't have this, just write it down. Okay, as you guys look at the quadratic, it should look exactly like something you graphed in Algebra 2. I'm not asking much more from you in that problem. I'm not saying you're perfect at it, but I'm saying this should look like a problem somebody could have asked you. If you glance over at the cubic example, it should look more complicated, okay? What about the cubic example is making it slightly more complicated? It's a cubic, okay, so we have to use a different parent function. Okay, it's got a negative, so we have to do a reflection. Cool. And there's a b value. This is not Algebra 2, okay? That adds a different layer. And remember that last week at the end of the week, we kind of saw what the b value did. And it was weird. It kind of did what a did, stretched and compressed and reflected. But it did it all for the x's instead of the y's. And it was like weird. When b got bigger, we actually pushed back towards the y-axis horizontally. And when b got smaller, we actually stretched things further away. It was a little bit stranger. So that might be a little different than what we're used to. So when you guys see something like this and you're going to graph it, what do we start with? Parent function, right? So you see the squared. You want to write the simplest table of values that already does the squaring for you. So if you guys were unaware why we always use the parent function, is because we want to do the squaring when the numbers are the simplest numbers possible. So here is something that does all of the squaring. That's my parent function. And again, that's something I know. Okay, so if you're sitting in your seat and you're like, well, she's a math teacher, so she just knows to write that down every time. The expectation is we all in this room would know how to write this down every time. We are used to the parent function. We've memorized it. We've seen it before. And if we have to rememorize it this unit, then we do. Okay? All right. Now we want to make a new table that takes into consideration the transformations. And we are going to ask you to write out the transformations. So we want to look at them here. So first, if you struggled with this last year, focus on splitting into horizontal and vertical, okay? Horizontal would be anything that's happening to x, and it would be something that if you plugged in a number, it would happen to the number before the squaring happened, because the x's are the numbers before they're squared here, and the y's are the numbers after they are squared, okay? So if I plug a number into this equation, what's the first thing that would happen to that number? I subtract the 5, right? The 5. Is the 5 happening before I've done any squaring or after? Before. So the 5 is affecting the x. It's horizontal, okay? But then after that, I would square. So the only thing that's horizontal would be stuff inside of here, which would be our 5, and that's our h value. Is h really a negative 5 or a positive 5? It's a positive 5 according to our formula, okay? So my new table is going to have an x plus 5 because h is positive 5, which means that my graph shifts right 5. The arithmetic in the table has to do the same thing that your mouth would say for the transformation. So if I'm reading a transformation that says shifts to the right 5, what kind of arithmetic would you do to move something to the right 5 on the graph? You would take the x and you would add 5 to it, okay? So that's what we're looking to do. The other things that are happening in the function here would happen after it was squared. So I would do something with the 5, then I'd square it. After I was done squaring it, I would multiply by 2 and then subtract 4. And we always do multiplication before we do any addition or subtraction. And we want to follow that same order of operations when we're setting up our table. So vertically, we have a vertical stretch by 2. So that means y is getting multiplied by 2. And then what is the minus 4 doing at the end of the equation? Good, it's moving the graph down 4. And if you wanted to move the graph down 4, so we also have a shift down 4. If I want to move it down 4, I need to subtract 4. I looked at the feedback you gave me, and almost every teacher did it this way. The only teacher I'm a little unsure of is if Miss Pinto actually had you guys like add the 4 and or add the 5 and subtract the 4. I couldn't tell by the information you guys gave me. So you guys might have only done this previously and then got a table, and then you started at like a new point and used those as measurements. We're making a table that's going to give us the exact points to plot on the graph. So we not only want to include the multiplication with a and b values, but we also want to add and subtract the h's in the case. So hope you guys are comfortable with that. And then remember what this means. This does not mean plugging anything back into this function. This means every x is getting 5 added to it. So I'm literally going to take the list of x's that I had before, and I'm going to add 5 to them. So the first x was negative 2. Negative 2 plus 5 turns that into 3. Okay. Negative 1 plus 5, 4. 0 plus 5, 1 plus 5, 2 plus 5. Is everybody okay with where I'm getting my x list? I didn't plug it into any function. I took the previous x list and I just transformed it. I moved all the x's to the right 5 by adding 5 to them. All right, now all the y values, I'm going to stretch them and then move them down 4. So every previous y value, like this one, used to be plotted 4. A y value of 4 meant 4 above the axis. Oops, I was trying to get rid. Sorry, guys, I'm dysfunctional. Okay, 4 was right here. I now want to stretch it further, double. So instead of 4 spaces, 4 times 2 would be 8 spaces. But then I want to take it and move it down 4, so I'm then subtracting 4. So I'm taking 4, timesing it by 2, so 4 times 2 is 8, and then I'm subtracting 4, so that gives me 4. And I'm going to do that with each of the numbers here. So is everybody okay with creating this table? Because the setup and creation of this table is the key way that I can get very quickly some brand new points that should make my new parabola. Okay, and if you're a little bit unsure, here's a couple of quick things you can check. Normally your vertex was at 0, 0. What did 0, 0 get turned into? In our new table, 0, 0 got transformed into what? 5, negative 4. Should that be our vertex point, 5, negative 4? Yes, and those of you that are nodding yes, tell everybody else in the class, what are we looking at to make sure that that makes sense? Good. Our h and our k value, 5, -4, makes sense for us to have the vertex. So I'm going to plot these points and make sure that they actually make a parabola that makes sense with all of my transformations here. And again, we're going a little faster than you would have gone in Algebra 2 because that was the first time you saw this. And here we're just trying to like build upon it. But remember, that means while you guys are working, if you're feeling like it was too fast, you're going to call me over to help you to make sure that I can clarify anything that doesn't make sense. Okay? And if you're like, I totally already know this, just consider yourself lucky that you will have to do less work while we are doing this. Okay? Is this okay with everybody? All right, so here's what I want you guys to do. I want you guys to take that graph that we just completed and try and go through and find everything in the chart except for the intercepts. You can leave the intercepts out for now. But HK, domain and range, increasing, decreasing, interval. You don't have to do rate of change or asymptotes, okay? But everything else on there, see if you can figure out those characteristics. While people are writing down those characteristics, I'm going to kind of take like a lap around the room to each group. And what I want to know is if there's someone at your group that doesn't understand how we made the table, like you're going through the motions and you're writing stuff down, but you're like, yeah, people are nodding their heads, so I didn't say anything, but I don't know where you're getting these numbers from. Ask me individually, okay? Yeah. Okay, we are going to come back and look at all the properties that you guys filled in. I'm not ignoring them. But while we're focusing on the graphing and the transformations, I now want to look at the cubic and make notes about how it's different than what we just did. Okay? So first thing, when you see a cubic and it's not a quadratic, you need to start with a new parent function, right? So I need to know my cubic parent function. If I don't know my cubic, I know I can at least plug these things in and cube them. And there's my cubic parent. Now here's where things are going to get a little bit more difficult because this function has a layer that your Algebra 2 version did not. Okay, it has that b value of 2. So the first thing I want you guys to remember from the investigation that you did on Friday, the h value here actually has nothing to do with the number 6, right? And that's because you've only studied x minus h exactly how I just said it, as x minus h, not 2x minus h. So the first thing you guys should do is you should rewrite this function so that the x minus or plus a number is separate from that b value of 2. Is that okay with everybody? That we need to see a group that by itself is x minus h, not 2x minus h, not 8x minus h, or a third x minus h, something like this, okay? So that affects our function in two ways. Thing number one, what is actually our h value of this function? -3. So it's actually a shift to the left 3. So I'm going to write these down as we do them. So shift left 3. Yeah. So I factored out the 2. Okay? Not all the way out of the cube, just separated it from, yeah, is that okay? So I took 6, divided the 2 out, and was left with 3 inside of that group. Okay? All right, so I shift left 3. Is that a horizontal or vertical change? Horizontal, so keep that in mind. What is the other horizontal change in this equation? What other stuff is inside and would happen to x before we cubed the stuff and moved on? Okay, good. There's this 2, and I like the way she said it. She's on top of it. So here's what you have to remember. We wrote this down, but this is a little tricky. It says 2. That means the number's getting bigger. But when you guys saw on the sliding scale on Desmos, when we made b bigger, we actually saw a horizontal compression. Remember what this means. X is getting to the y's 2 times faster, but that means I actually have to use less x's along my axis to go up further. So we don't use it like a 2. So it's horizontal. Is everybody okay why I'm writing horizontal down? Because it's in there with x. then before you say stretch or compression, I want you to think about how we're going to use the 2. We don't actually use the b value like a 2. Instead, we made a note to ourselves to use the reciprocal. What's the reciprocal of 2? A half. If you're multiplying distances by a half, even though there's a 2 in the equation, what's going to happen on the graph is the distances are going to get multiplied by a half. Is that making things smaller or bigger when you multiply them by a half? Smaller. So the words I should say are horizontal compression, because I'm actually going to be using a half. Okay? Does that kind of give everybody at least a strategy to make that decision? You have to remember how b works. There's kind of no way around that. So when you see the 2, be like, yes, in the equation it's a 2, but the way it's used on the graph is a 1/2, and then translate that into what that means. It's horizontal because it's happening to x, and if I multiply things by a half, they actually get smaller, so the word that goes with that should be compression, not stretch. Okay? All right, those are the only horizontal things, and so here's what that will look like to our x values in our table. Is everybody okay why I just wrote the header on the table for the horizontal values, the x values, to now be 1/2 of what they were before, and then -3. I'm trying to compress them by a half, and then move them to the left 3. Okay? It's just like an a value. It just doesn't work as simply as the a value. Okay? It does the same types of things, but kind of the opposite of what you think. Is that all right with everyone? Okay, so if you're going to relate it to something related to the a value, but have like a little asterisk next to it, which tells you it works a little bit differently, right? All right, now let's look at all the vertical stuff now that we finished that. And here's the good thing. The horizontal stuff is a little bit whack. Like, it says x plus 3 in our equation, but really that means we move to the left 3. And it says times 2, but that really means on the graph we times things by 1/2. So basically all the horizontal stuff is kind of not exactly what it looks like in the equation. What it means in the equation is slightly different than on the graph. The vertical stuff is exactly what it looks like. If you see, okay, first we have a negative out here. What does multiplying by negatives, what kind of transformation does that cause? Should cause a reflection. Now, this negative is out of the cube. This negative is out of the cube, meaning it's supposed to be affecting y. And if you're not sure which axis that means it's over, think about it. Okay? I know that this has something to do with y's and it's supposed to be reflections. Here's positive y's. What happens if you make them all negative? They go down here. Here's the negative y's. What happens if you make them all positive? They go up here. So even though I'm changing the y, which axis am I reflecting over? The x. Did you see which way my hand just moved? Okay, moving things from above to below is reflection over the x-axis. And then there's a -4 here, which again is a shift down 4. So it would look like this. So our y values are a little bit easier to change here. Okay, we just have to take their opposite and then subtract 4. So -8 would become +8 minus 4. -1 would become +1 minus 4. 0. +1 would become -1 minus 4. And I know I'm doing this part a little bit quick. That's because I think you guys can do the arithmetic, but it would look different for all of us. Some of us do it in our head. Some of us are writing it all out. Okay, I'm not discounting any of those methods. I'm just trying to let you check whatever method you used before, and are you getting the same numbers that I'm getting here, okay? So those are the values that I'm getting. And then for x, it's a little bit harder. I have to multiply by a half and then subtract 3. So I'm going to kind of do each one off to the side here. So when we plug in -2, those of you that are not good at fractions, they're not going to go away, especially now that you're doing this horizontal stretching and compressing, which uses the reciprocal, right? Which means if you have a fraction in there, it gets flipped over. It wasn't a fraction. Now we're using it like a fraction. So we're going to have to be okay with this. When you plug in -2, first make it a fraction, okay? Then remember when you multiply, straight across, okay? So 1 times -2, -2, 2 times 1, 2. Reduce if you can. So what's -2 over 2? -1, and -1 minus 3 is -4. And now I'm going to try it again, but this time I'm going to plug in -1. So 1/2, 1/2 times -1 minus 3. Again, make it a fraction. Multiply straight across numerators and denominators. It can't reduce. Now you have to do fraction subtraction, okay? With addition and subtraction for fractions, the key thing is you need a common denominator. So I'm going to think of 3 as 3/1. I want it to have a denominator of 2, so I want to multiply the 1 by 2 to change the denominator into 2. But then I have to do that same thing in the numerator so it becomes 6. So the common denominator is 2, and the arithmetic in the numerator is -1 minus 6, which is -7. Okay? And what is -7/2 if that makes you scared to plot it on the graph? -3.5. Just do 7 divided by 2. Okay. 0 is a little nicer because 1/2 times 0 will just be 0. Okay? And 0 minus 3 will just be -3. Then I plug in 1, okay, and I go through this whole thing again. So I get +1/2 minus 3. Again, make the common denominators 2, and the numerator is 1 minus 6, which is -5. If you're scared of -5/2, turn it into a decimal.
Oh my gosh, you were the same thing I did.
did. You're on my recording right now, just so you know.
That's great.
Hi.
You look wonderful today.
You look amazing. I can't believe we had the same clothes in our closet.
What? And especially neon yellow.
Right? I wear it every day. Okay. Miss Patterson, everybody. Little cameo appearance. She scared you? She's very peppy. She thinks I am like low-key peppy, but I told her she doesn't even, like, have you met her? She's very peppy. Okay. It's all being recorded right now for humanity's sake. All right, so I plug in the last thing. It works out nicely. I get 1 minus 3, which is -2. Sorry for the interruption. Okay, now go ahead and plot these points. Okay, so -4, 4. We're going to make sure they make sense. -3.5, -3. -3, -4. -2.5, -5. And -2, 12. That's off my graph. It's like down here somewhere. All right, now, a couple, yes, sorry. Yes, yes, okay. So question number 1, super good question, super useful for you guys. All of your tools are only as good as you. So like your graphs, your calculators. She said, can we scale the graph? So like if you have halves or thirds or something and you don't like it, you totally can just make it very clear what you rescaled it by marking it on the graph or make a note off to the side. Okay, Jake?
We're going to use calculators like in a quiz or something instead of having.
No. This test will be no I know it's really brutal to ask somebody to multiply by 1/2 and then subtract 3. I'm asking some pretty intense things, okay? It was worth a try. You guys are all hating on him, but you all were hoping the same thing, okay? All right, but no, I do expect. He did. I will be fair in the fact that this is my biggest expectation, that you have to multiply by a fraction and then possibly add it to something else. So you have to make a common denominator or whatever. But yeah, you should be able to do that part by hand. You're not going to be allowed to use a calculator because you're going to have to find intercepts and stuff like that. Shh. And I want you to be able to show me that you can do the solving, that you didn't just plug things in and check them, especially with like a graphing calculator or something like that. Things that you should make sure of on your graph. First thing, did your HK end up where you expect it to end up? So it was 0, 0, and now it is -3, -4. Does that match our H and K values? Yes. Okay. Does the graph look how it should look? So what I mean by that is you were graphing a cubic. Does it still look like a cubic? Yes. Yes. And the major differences that I see based on the original cubic function are that number 1, it's flipped the other way. Is that okay? Did we do something that would have flipped it the other direction? Yeah, there was a reflection. The second thing I see is that it kind of looks like it was vertically stretched, but we didn't have a vertical stretch. But what we did have was a horizontal compression. Make sure it makes sense at the end. If you wrote down the words horizontal compression, does this look like the basic cubic and somebody went like that to it and squished everything closer to that middle point? Okay, and it does. That would have the same effect that a vertical stretch has. Okay? All right, so go ahead. For the last few minutes of class, you guys are going to fill in the characteristics. Don't worry about the intercepts. We're going to work on that tomorrow.